having me. Yeah, so I will talk about autoregressive reasoning, about PAC and online balance. Thank you for the introduction of the topics. Basically, the only thing I assume is that you know what is PAC-learning and online learning, which you covered. Thanks. Besides that, I'll define everything. Okay. So again, this is based on two works. One with Steve Haneke and Shai Morad. This is about the PAC setting, and the other work is with Idan Mehalel and Hanan Mosel about the online setting. Okay. So as you can see, if you read the title, basically there are two special terms that some of you might not know. I guess everybody knows what's PAC-learning, what's online learning, but autoregressive and chain of thought are relatively special or new terms. So I want to start with explaining what are those terms, what is the motivation, where are they coming from, and then we'll give some informal motivation for the questions we want to ask. Then we'll give some high-level answers, and then we'll dive a bit more technically into the definition and results, and even some of the proofs. And actually, the introduction was good because you had this picture with the graph, right? Sorry, had this picture with big graph, so we'll see how one of the technical formal proofs is actually very similar to the same. Okay. Okay, so let's start with the first term, autoregressive. So basically the motivation comes from the world of LLMs. So basically LLMs are basically, maybe in today's LLMs there are some other parts, but basically LLMs are the basic mechanism is an autoregressive next token generator. I think I had a similar slide. So what an LLM does, it gets some context, which is just a string, and then it applies itself on the string and generates some next token, which it thinks it's most probable, most suitable, and then it appends this next token to the original context and applies itself again, generates another token, appends it, and so on and so forth. This is the way it continues. So this is why it's called autoregressive generation, because it applies itself and it predicts by applying itself again and again. So this is the autoregressive part. Now, why chain of thought? How chain of thought gets to this story? Okay, so basically we start from an empirical phenomenon that shows that chain of thought helps LLMs to do better, to achieve better results. So this is a screenshot showing an experiment result of one of the first foundational works on chain of thought reasoning. You can look it up. There's 30,000 citations. It's called Chain of Thought Prompting Elicits Reasoning in Large Models. So basically their idea here, and you can see they compare between standard prompting and chain of thought prompting. So they call it standard prompting, but actually it hides some technique which I guess is pretty known to people that works in LLM trading. So they call it standard, but actually it's called few shot prompting. So as you can see here, they want to ask the LLM a question. For today LLMs, it seems like a very easy question, but the LLMs of 21, 22 made mistakes on those type of questions. So instead of just directly asking the question, in few shot prompting, you give similar examples inside the prompt of question and answers, and then you ask a similar question, and this should help the model give you the correct answer, but in this case, it didn't work. But once you give the exact same question and answer, but as part of the answer, you give the entire scratch pad of how, like a possible way to get to the answer. Roger started with blah, 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 and you get to the final answer by this explanation, which is 11. And then in this case, their experiment, this specific experiment, shows that the model got the correct answer now. And note that not only that it got the correct answer, it copied this behavior of explaining and explaining the thinking, the entire chain of thought that led him, not him, led it to the correct answer. Okay, so this is an example for how chain of thought helps. But here you can see that the chain of thought is given as a part of the prompt itself, which is not exactly what we do when we analyze sample complexity or mistake bounds theoretically. And then we talk about training usually. So later works took this idea and integrated in the training of the LLM. So for example, this work, the COT for chain of thought collection, took many examples and integrated in the training process and showed how it works, how it helps the LLM. And this is done usually via a process called supervised fine-tuning. So basically the idea in supervised fine-tuning is that after the LLM is trained on many basic or like cheap examples, you can generate a very high quality set of examples, which could be smaller but just much more high quality examples, and you feed those examples to the LLM as part of its training, not as we've seen here. Not as we've seen here, just as part of the prompt, but actually as part of the training itself. And this begins to be more similar to stuff we do when we analyze sample complexity of algorithms. Okay, so the desired result from this process is an autoregressive model. As we've seen, the LLM is an autoregressive model that uses the chain of thought reasoning method. So it uses a series of intermediate reasoning steps that leads to a final answer, right? Exactly as we've seen here. So not only that that it got the correct answer, but it actually uses this idea of intermediate reasoning steps to lead to the final answer. Right? Yeah.
So can you go back? So you want the final answer, but not the beginning, right?
Yeah. So we care about the final answer, but we see that it copied this idea of explaining using the intermediate reasoning steps, and we can imagine that this is at least one of the reasons that helped the model to get the correct answer, because without it, this is the only change you. I mean, this is of course just intuitive, just one example, but in their paper they have many examples. Great. So this is basically the empirical motivation for this line of work here, at least as I see.
So if we summarize, when you say you want to slide back,
yes.
When you go to supervised fine-tuning, what basically is you created your input has a chain of thought,
Exactly.
And the model
Exactly.
is continue that chain of thought.
Yeah.
That's the supervised learning. The supervised fine-tuning.
No, so you give examples that actually contain the chain of thought. You give like a super complex integral that you want to calculate, and instead of just writing the answer is 13, you write the entire scratch code of how you can calculate the integral. It's part of the training. So you give many examples, then you ask the model to calculate and use. Okay. And then it can use the chain of thought examples to calculate. Okay, so this is the empirical motivation. Now, to formally study this model theoretically, Joshi et al. In CoLT last year defined this PAC-style learning model for autoregressive learning with chain of thought. So that they defined it as follows. So given the next token generator, this can be thought as the LLM. So it receives some binary string, finite binary string, and it outputs only one bit. Okay, this is a simplified model. It outputs 0 or 1, but this already captures a lot of interesting problems. We know that even binary functions can be hard to learn. And the autoregressive process is exactly as we've seen in the LLM example. So for some input x, which is a question, a prompt, a binary, some binary string, f applies itself on x and generates a bit, and then it appends this bit y1 to x and apply itself again on x, y1, generates y2, then apply y1, y2 to x, and generate y3 from applying f over x, y1, y2, and then we get y3. So in this case, those are 3 chain of thought steps that generates the chain of thought y1, y2, y3, and the final answer, which is the final bit, is y3. We denote it by f e to e for n to n with t steps. In this case, t is 3 over x. And we also denote the entire chain of thought by f COT t over x, which is the entire chain of thought y1, y2, y3. And the goal is always, as we already said here, is to learn the target end-to-end function. So, what is the target end-to-end function? So we have some given class as standard learning. We have a class F, large F, calligraph F of next token generators. And one of them is the target next token generator. And for every such F, we can define the end-to-end function, as in here. And then we can define the end-to-end function class by all of those end-to-end function. And we want to learn the end-to-end function induced by the F star, the target next token generator. So this is our goal, to learn this end-to-end function. Okay, this is like the perfect LLM or the ground truth, the perfect end-to-end answers of the perfect LLM. Okay. Now I want to give another example which is more fixed, more suitable to this theoretical model. So I want to do two things in this example. Okay, first of all, are there any questions on this model? It's clear why this is like the same. Okay. So I want to do like a couple of things in this example. First, I want to show that the simplified model is meaningful. It captures difficult problems, and I want us to like start thinking about what are the natural questions to study in this model. So a motivated example is determination problems, which we can model because we have the end-to-end answer is always a bit, 0 or 1. So here's an example. We can give the model the prompt. Does the quest the following as prompt the following question? Does this graph contain a Hamiltonian cycle? Everyone remembers what the Hamiltonian cycle is? Okay, so Hamiltonian cycle is a cycle in the graph that walks only, of course, on edges and visits every node exactly once. Okay, so this is the question, and let's see an example of how the model F can reason on this question, on this prompt. So it starts by looking for a Hamiltonian cycle. Okay, so you can follow what it does in the reasoning step. So let's say it starts from 4, then it goes to 1. In the second step from 1 to 3, and then from 3 to 5, and then from 5 to 4. Then it sees that it didn't go through 2, so it starts again. It starts from 4 again to 1, from 1 to 2, from 2 to 3, from 3 to 5, and from 5 to 4. And then it sees that, okay, it found an Hamiltonian cycle, so the answer is yes, and it starts outputting yes. Until it gets to the final step, 13, we did t being 13 here, and the end-to-end output is 1.
This nesting is just so you don't have the problem that of a fixed t, right? Why do you have this less behavior that it keeps saying the yes? Because
Yeah,
we
because
don't need to.
once you reach the answer, you don't need to keep
It's like a
reasoning,
state
so you
machine.
just continue to output the final answer because the end-to-end is always the final. Okay. Otherwise, you would need to change.
And
T.
then the equivalent you say the T is up to
Yeah,
a
right,
certain.
yeah, it's good. Yeah. Okay, so here are two things I want us to take from this example. So the first thing is the importance of taking T to be relatively large. So let's think about what would happen if T was just 5. So if T was just 5, the model would still be in the middle of reasoning and the final answer would be 0. It's not really the final answer because it's still in the middle. So what I'm trying to say is that intuitively, it makes sense that more difficult questions requires larger and larger values of T. And as you increase T, you give the model the opportunity to answer more and more difficult questions. You can also see it like intuitively empirically. When you ask the LLM question, as long as the question is harder, it needs to think more. So this is one thing. So what do you think a natural question would be? Do you have any idea, like in this context of larger T lets you answer more difficult questions? So a natural question, I think, is to ask, as you increase this T, what is the sample complexity of learning this class, F entering T? Because as you increase T, the class, you can pick a target function that can successfully answer more difficult questions. So it makes sense that as long as your class can answer more difficult questions, it will be more difficult to learn. So this is one question that makes sense. How does increasing T affect the sample complexity? And the other question comes from this idea. So basically, we have this example can produce two types of feedbacks, two types of supervision, right? We can give end-to-end examples, which means just the answer and the final answer, saying that yes, this graph contains a Hamiltonian cycle. Or we can give as example in COT supervision this question and the entire chain of thought. So if we give the entire chain of thought, the model won't only receive the answer that there is a Hamiltonian cycle, it will receive the entire scratchpad of how the target function found the Hamiltonian cycle. It sounds much stronger. Okay. Question? Yeah.
This example, the intermediate outputs are the reasoning and the step output.
No. This like intuitively explains what the model does. Like, and this is the output of the step. So 1 says you're in the right way, you can continue, and 0 here says no, this is not a Hamiltonian cycle, you need to find another way.
By feeding the intermediate step outputs, the model does not have the past reasoning, so how can it use it for feeding the expectation?
Sorry?
If it gets feedback only the step output, how can it use the past reasoning in order to use it for completing the computation?
Oh, yeah, right. This is a simplified. I mean, if we want to do it accurately, you need to like make this more explicit. You need to encode every specific reasoning as an intermediate. This is just like intuitive.
It's not an example of the formalism of the binary model.
Almost, because you just need to encode the entire reasoning and not just like the result.
One if it's first.
I actually disagree with you and agree with him in the sense that if you go back, you're assuming that F star is a function of the previous outputs. There's no notion of scratchpad in your formalism. So F receives as input X, Y1, and Y2.
Mm-hmm.
It doesn't receive anything other than the binary bits generated
Right.
by itself. So it doesn't receive the middle column.
No, yeah, okay.
You're only
Sorry.
allowed to add bits if they were output of your models. You can't just add bits that were intermediate
Okay.
computations.
I mean, this is not. They're not really three columns. Actually, they're just a step and the output. But you can encode this entire step as binary bits, right?
Maybe you should have made it as like 100 bits that encode that text. Maybe that would make it more
Okay.
right.
But
Form goes to one can be encoded in bits.
so the model sees okay, it started to walk from 4 to 1. Like the model has an internal reasoning that knows, okay, those bits are saying I
You
started.
don't think those two should be separated formally? The internal reasoning, there's the internal reasoning and the step out like you had here, which do seem like very different things. And in the formalism, you just have F that you see this input a bunch of bits and doesn't distinguish between these two things.
Yeah.
Doesn't seem like the right formalism, but okay.
Okay, I mean, okay, let's, if it wasn't clear, I don't think this model really represents an LLM, maybe like from the simplest reason that the function here is deterministic. So this is just, I think it's in the level of inspiration. I think it makes sense, but I agree that, yeah, this is not like this. For me, this is a way that this is clear, but it's not very accurate. Yeah.
You said that the sample complexity should scale with T because for more difficult problems you need more reasoning steps. But
Intuitive. I don't know.
But isn't this logically actually the reverse? Because what the sample you can take very easy problems and run arbitrarily large number of reasoning steps on them. So it's not that that T scales with sample complexity because you need higher number of reasoning steps for harder problems. It's the other way around. Maybe there's a notion of a minimal T for that's needed to achieve certain sample complexity.
Okay, just saying the following. If we agree that a longer computation time, longer reasoning steps, a larger number of reasoning steps allows the model to solve more complex tasks. So it makes sense that learning a target function from a more complex task takes higher sample complexity. Just think of the class of all functions. So this has infinite sample complexity. It's unlearned, right? So, but in the middle, as you get closer and closer to it, the sample complexity increases. You're not convinced. Okay. Sure. Okay. So now after yeah, great. So I just wanted to say, so basically the second question, I think it's natural to ask. It seems intuitive that if we give the model the entire question and entire scratchpad towards the solution, the sample complexity could decrease. It could help the LLM to learn. So the second question informally could be how much giving chain of thought examples instead of just end-to-end examples would help the model to learn. Now, to discuss those questions formally, we need to make some definitions, to give some definitions. So first we define the two supervision models. So as we already kind of said, we have end-to-end supervision, where the training examples are just the prompts, X, and the end-to-end examples given by the end-to-end version of the target generator F star. And we have a chain of thought supervision where the training examples are the prompts and the full chain of thought over every input that we receive in the training. And I remind that the goal is always to learn the target final answer. We don't care about what happens in the chain of thought, we just care about the final answer. Now we can discuss the thing a bit at the technical level. So at the technical level, note that since our training examples are just x and f star e to e x, and we are measured, we want to learn f star e to e x, so this is just standard learning of the class f e to e. Okay, so learning with end-to-end supervision, just equivalent to standard learning of this class, of the end-to-end iterative class. But this is not true for chain of thought supervision, because in chain of thought we're measured, the test is over the end-to-end function, but in the training we get more information, we get the entire chain of thought. So this is not a standard learning task where we get examples and then tested on the same function that generated the example. So for all we can know, for all we know, learning with chain of thought could be much easier, or it could be the same, or somewhere in the middle.
Do you assume only a single reasoning example? Because there can be many equivalent reasoning traces that lead to the final same answer. So during training,
you have a target next to token generator, and the example is generated by doing this autoregressive.
In your supervision during training, there could be many reasoning chains that lead to the final answer. So what do you see during training? Do you see only
Here
one?
in the chain of thought? No, because the function is deterministic. You just have one. You just have one thought, right? Okay, so these are the supervision models. So now we discuss two settings for this supervision model. One, basically those are the two fundamental learning settings. We have the standard PAC-learning setting, and we have online learning. And in both, we can discuss both end-to-end supervision and chain of thought supervision. So in the PAC setting, we are measured by the mistake probability, as Noah previously defined. And as we said, end-to-end learning is equivalent to learning the end-to-end iterative class. So as we know, the mistake probability is characterized by the VC dimension of this class over the number of examples. And in the online learning setting, again, so this is just online learning, the class, the end-to-end iterated class. So the mistake, in online learning, we're measured by the mistake bound. And the mistake bound is characterized by the Littlestone dimension of the end-to-end class. I guess everyone knows VC dimension. Okay, but maybe not everyone knows Littlestone dimension. Not everyone. Okay, so think about this as like an equivalent of the VC dimension for online learning. So VC dimension characterizes the mistake probability, and Littlestone dimension characterizes the mistake bound in online learning, and we will define it later when we'll need. And in the chain of thought supervision model, so the same. It's exactly the same. In the PAC setting, we are measured on the mistake probability, and in the online setting, we're measured on the mistake bound. But since those are not standard known learning tasks, we don't have those combinatorial quantities that characterize those quantities.
Just make sure mistake probability here, it means that even a single bit out of the y1 to yt does not match the original COT. That
No.
is the loss.
No, because you're measured only, this is why it comes here every slide. You measure only on the final answer. You don't care, even if every bit except for the last one is incorrect, as long as the final answer is correct.
So you include the assumption that the final bit of f star COT is equal to f star e to et, right? Because theoretically it could have been that the best one, that one and that one would not be the same.
No,
right?
no.
Because
let's
it's
get back to the definition, right? Because the chain of thought is the entire bits generated in the t-step process.
So define to be the same. The last one.
And the end-to-end function is just the last bit of the chain of thought. Okay? Think about the way a student asks you a question and you explain the answer, and then you just define the final step of your explanation is the final answer, right? So this is exactly the same. Okay, is that clear? This is like important. So, okay. Okay, so these are the settings we consider, and now to be more convenient, instead of talking about mistake probability and mistake bound and whether it's VC and not VC, we'll just define a notion we call a learning rate. Okay, so the learning rate is just the quantity that tells how good the learner is. Okay, so R is the learning rate of a PAC-learning task. If its optimal mistake probability is R over the number of examples, so the mistake probability is characterized by R, and R is the learning rate of an online learning task if the optimal mistake bound is roughly R, up to constant factors. And we're interested just in the learning rate of all those 4 examples we have just discussed. Okay? So, again, in the end-to-end statistical task, PAC-learning task, we're interested just in the VC dimension of the end-to-end class, and in the end-to-end online learning task, we're interested in the Littlestone dimension of the end-to-end class. And in the chain of thought supervision model, we are interested in the PAC rate, which has no known quantitative combinatorial characterization. And in the online COT supervision, we're interested in the online COT learning rate, which again has no known combinatorial characterization. And now we can actually formally state the questions we asked informally. So we have a learnable class of next token generator F. Okay, so in the PAC setting, learnable means that the VC is finite, and in the online learning setting means that the Littlestone of F is finite. And we ask, how does the learning rates of the end-to-end learning the end-to-end class under end-to-end supervision scale with T? So as T grows, what happens to the learning rates? And the second question we discussed was by how much chain of thought supervision helps. So by how much the COT learning rate is smaller than the E2E learning rate in the PAC setting and in the online setting. Okay, so until now we discussed about motivation, defining the model, and defining the questions we are interested in. And now I will present the answers, like the answers we have, we know, and discuss like 1 or 2 of the proofs, and that would be it. So any questions? Are the questions clear? Because we're going to now present the answers we have and discuss the proofs. Yes.
So,
yeah, sure.
Motivation for this kind of question, for example, what information is asked?
What information? What? Sorry.
What information like the R.
What information do I have, like in the training process?
For this term or this arching of thought T tag F.
What is the motivation?
Yeah, what it gets asked. What it gets asked. If we have.
If this is much smaller than this, and what it tells us.
Yeah.
So it tells us that chain of thought helps. If it's not smaller, then it tells us theoretically the chain of thought doesn't help. Okay, so do you have a guess for the answers?
Much smaller.
Okay. So let's start. So what happens in the... So those are just high-level answers, and then we'll dive a bit more deeply into the answer. So in the end-to-end learning test, the learning rates landscape is very rich. So essentially, there is a class realizing any rate within some range. So in the PAC setting, the range of the possible learning rates is between 0 and VC dimension of the base class. When I say base class, it's the class of next token generators times T. So it's linear in T. And in the online setting, it's between 0 and the Littlestone dimension times log T, where T is the number of intermediate reasoning steps. So let's parse this range. It means that for every function that behaves asymptotically as something in this range, you have a function class of next token generators, such that as you increase t, the VC dimension or the Littlestone dimension of the end-to-end class behaves as this function. Okay, so this is for end-to-end. And for chain of thought, we show that the landscape completely collapses. So for every learnable class, the learning rate is just constants that depends on the class. So there is actually no dependence at all at t once we have chain of thought supervision. So intuitively, this is a pretty optimistic message, because we said that intuitively, as we increase t, this should allow the model to solve more complex tasks. And this basically says that when we have chain of thought supervision, we don't pay in accuracy. So the same sample size will allow us to solve more and more complex tasks. Meaning we can learn the end-to-end iterated class as t increases and increases without paying in the sample complexity at all. So how this makes sense? Well, I mean, where do we pay? So we pay in the training process, right? It makes sense that getting training examples for more and more for questions that are getting difficult and more difficult, which means that t gets larger and larger, is more difficult. So instead of paying in accuracy, we're paying in creating examples that has very large chain of thought. So it doesn't really come for free. Yes.
Can we create a class function class f such that as we increase the number of steps it can auto-regress, its expressivity goes to infinity? But that has a finite VC dimension, but if you allow it to operate over itself as many times as I want, its expressivity becomes arbitrarily large. It sounds intuitive that it should be, but if that's the case, then it's impossible, because now you're saying they can learn an arbitrarily large VC complexity with finite number of steps.
So
of examples.
Maybe, but as you increase t, you also the amount of information that you give to the learner in every example increases. Think about it like that. Because how the process works. Let's go back to the beginning. So the process goes as follows, right? We apply, so in t steps we apply f for t many times. So in the chain of thought supervision model, once you give one example, you actually gave t example, not IID examples, but every one example encodes t example. So maybe the expressivity goes to infinity, maybe, but also every example encodes more examples. So this, I don't think it contradicts. Make sense? Oh. Good question. Okay, now, so those are the high-level answers, and let's dive a bit more deep into those answers. By the way, how much until what time I have?
20 minutes.
20 minutes? Good. So, basically, our beginning point is this theorem from Joshi et al. 25. They defined this model. So they show that the VC dimension, which is basically the learning rate of the end-to-end class, is at most the minimum between the VC dimension times t and the Littlestone dimension times log t, which implies that if the VC dimension of f is finite, then the VC dimension of f e to et is finite. So learnability of f implies learnability of f e to et. But there's a linear dependence on t, which could be extremely large. But they also show that the VC term is tight for some classes. So there are classes which you really need a VC of f times t sample complexity. And when I write online paper or PAC paper, these are the papers that talk is based on that I presented at the beginning. So from our online paper, we show that the Littlestone dimension of the end-to-end class is most Littlestone times log t. So this is the analog result of the PAC setting that they proved. And we also show, similar to as in this theorem, we show that this is tight by showing that there are some classes for which the Littlestone dimension is at least Littlestone of the base class times log t. And in fact, we show that even the VC, that for those same classes, even the VC dimension grows as log t, which also shows that their second term is also tight, which is mu. Okay, so those are like two worst case upper bounds. So the upper bounds always hold, and the two theorems show that for some classes they are tight. But let's think about the other extreme. So it's not very hard to show that there are some classes even with infinite Littlestone and infinite VC dimension. Translation to if someone is not familiar with Littlestone dimension, to infinite Littlestone dimension means that there's no finite, any learner will make infinitely many mistakes in the online setting. So there are classes which are not learnable in the PAC setting, not in the online setting, but for every intermediate steps, once we make at least two intermediate treatment steps, the VC of the end-to-end class and the Littlestone of the end-to class drops to 0. So very briefly, why this makes sense, because you can take a class which is very complicated on a large set of instances, but outside of this large of instances, it's very, very simple. It always outputs 0. So once you append anything to those set of instances, then the class complexity completely drops to 0. So we have some classes where the class completely becomes degenerate after just 2 computation steps, but we have classes where the end-to-end class gets very complicated as we increase it. So it's natural to ask what happens in the middle, like what rates are possible between 0 and log t, between 0 and linear t. So as I already said in the high-level answers, basically everything is possible. But we need to define what exactly I mean by everything, because it's not really everything. There should be some definition. But we show that the definition requires very, very mild assumptions. So we define a specific set of possible growth functions, growth rates, which are monotone and subadditive. So a growth rate is monotone and subadditive if it's non-decreasing, meaning that R is the rate. R of T1 is, if T1 is smaller than T2, then R of T1 is smaller than R of T2, and it's subadditive. So R of T1 plus T2 is always at most as R of T1 plus R of T2. So all of those functions looks like a step function, because the function is from natural numbers to natural numbers. So all of those functions looks like step functions, such that the step length only increases. Steps length never increases. So if you imagine it, basically it's like every one line natural sublinear function. It's most linear function. So as long as you don't do crazy things and functions with functions with cases, right? As long as you don't have cases, just have functions that behaves as square root t, t to the 2/3 or whatever. So any such function satisfies this definition. So the theorem we show is that for any such function, for any monotone subadditive rate, there exists a class f of next token generators such that the VC dimension of f e to e t grows as this rate r of t. And for the online setting, we show roughly the same, but for sublogarithmic rates. So we say that a monotone subadditive rate is sublogarithmic if on top of the other demands we had before, it satisfies r of t is less than log t for any sufficiently large t. And then we show pretty much the same theorem that for every monotone, sub-additive, and sub-logarithmic rate R, we have some class such as the Lilstone dimension of the end-to-end class scales as R of t. And for logarithmic rates, rates that grows not sub-logarithmically, but exactly logarithmically, meaning that grows as some constant times log t. So for every natural d, we have a class f, for which the Lilstone dimension is just d, but the Lilstone dimension of the end-to-end class grows as d log t. So because of our worst case upper bound, we had that are linear in t from the Joshi et al. Paper and the logarithmic in t in the online setting from our online paper, then basically those theorems establish a complete taxonomy of all possible learning rates we have without chain of thought supervision. So the message is that for any learnable class F, we can bound the sample complexity or the mistake bound of the E2E iterated class. But not only we can bound it, for everything in the middle between 0 and the upper bound, there is some class for which this is the rate. So they are basically in nature we have many behaviors of how the sample complexity increases with t. And I don't know, maybe it's a bit related to what you said before, that for some tasks the way the sample complexity of the iterated class grows with t is relatively small, and for some classes which encodes really difficult tasks for which you really need to grow a lot with t, the sample complexity really need to grow a lot with t, then the sample complexity of the iterated class grows as a larger function. Okay, so this is learning without chain of thought. And for learning with chain of thought, so the bound that was established in the Joshi et al. Paper that introduced the model was that once we have chain of thought, the sample complexity drops from at most linear, as they showed, to at most logarithmic with t, but they still have this dependence on t. And what we showed in both of the papers is that both the PAC-learning rate and the online learning rate is actually just a constant, the dependence on the class, and there's no dependence on t at all, not even logarithmic. Yeah.
I'm trying to figure out how to align the two perspectives. So, if I understand correctly, there's nothing in your framing that connects so you have a family, the function class is f from 0, 1 star. Mm-hmm. And there's nothing that requires connecting what is the family of the functions from input size 10 to input size 11. They can be arbitrarily different functions, theoretically. Right? I mean, in practice, if it's a network, it will behave somewhat similar, but in your theoretical framing, like the family of functions from input size 10 to the next one might be linear regression, and the 11th one might be binary trees, and anything can happen.
Yeah, you have a limited number of instances.
So that's the complexity. So, in a sense, what you're saying is that when you learn end-to-end, you are learning just the combination of a bunch of different. There is no VC of F is sort of maybe not the right way to think of things, because these are different families of function that you just chose to chain in a certain way, versus in chain of thought, like you see all of them, so you sort of simultaneously learn every step. Okay.
I'm
not sure what's the question.
That's a good question. Actually, we kind of thought about it, like what happens when the class, because it's more like no, I think it makes sense to take a learnable class. The class is not learnable, so basically it means that, okay, when you take t equal 1, then this is the same as standard flow. So the class is not learnable, so already in t equal 1 it's not learnable, there's nothing to do. But since we have classes that gets completely degenerate after some t, so maybe it does make sense to think about the case of infinite VC, but we have in the paper like a partial justification for handling only VC. So you can take classes with infinite VC dimension that actually does, I think, what you said. That are completely like whack between. So the sample complexity of the end-to-end class could be 0 for some t's and infinite in others. It keeps alternating between trivial and infinite. So it doesn't give complete justification because there could be a better combinatorial characterization that avoids this, that lets you know exactly what classes are learnable in each t's, but we don't have it yet. But yeah, it would be great to have such a okay. So let's say a bit what are those constants really quickly. So in the PAC setting, the constants are the minimum between VC of f times dual VC of f and the Littlestone dimension of f. So dual VC of f, is that something known? Yeah. So dual VC of f just means the VC dimension of the dual class. I won't get into it because it's a technical thing, but the dual class, actually it's pretty useful. You can read about it. The dual class is just taking the instances and the functions and switch roles. It's not understood, just read about it. So VC star is the VC dimension of this class. And the VC times VC star terms comes directly from a nice sample compression argument from like 10 years ago in one new class. And something to note is that the VC star of f is at most 2 to the VC of f. So this means that as long as VC of f is finite, is a constant, then VC of f times VC star of f is a constant, which is why we allow to write the constant here. And in the online setting, this O of one term is simply the Littlestone dimension of the base class. Okay, so to sum up, when we have no chain of thought supervision, then basically in the PAC setting, anything between constant and linear dependence on t can happen. In the online setting, anything between constant and logarithmic can happen. And once we add chain of thought supervision, then everything becomes just a constant. Okay, now let me like very briefly talk about a proof idea that I think explains how exactly chain of thought can help. With just one example, okay? So let me talk about the separation for Littlestone classes. So for now, I just assume that a Littlestone dimension, which I will in a minute define for those who are not familiar with it, the Littlestone dimension of the class is finite, which means I only talk about classes that are online learnable, which means there is a learner in the online setting that has finite mistake count for those classes. So we have this separation for every learnable class F, or every class with finite Littlestone dimension. The PAC-learning rate and the online learning rate with COT supervision is at most Littlestone of F, but there exists a class F such that the Littlestone dimension is a constant, like 10, but for every t, the learning rate of online and in the PAC setting without chain of thought supervision grows as log. Grows as log. So let me discuss the separation a bit. So to explain the separation and the proof idea, I need to explain briefly what is the Littlestone dimension. So let's explain it by an example. So let's take the class of thresholds of over 1, 2, 3. Okay, so our instances is 1, 2, 3, and our functions are the 4 thresholds, meaning everything is 0, or a threshold between 1 and 2, or a threshold between 2 and 3, or everything is 1. So the interesting object when talking about the Littlestone dimension is a Littlestone shader tree. What is a Littlestone tree? It's a binary tree such that in every edge, on every left edge we write the label 0, on every right edge we write the label 1, and in the nodes we write instances from the class 1, 2, or 3. Okay, and every branch is realized by our class if there is a function, a hypothesis from the class that agrees with the branch. So with this branch, meaning this branch gives the label 0 to 2 and the label 0 to 1. So it is realized by H0 that gives 0 to everyone. And this path that gives 1 to 2 and 0 to 3 is realized by H2. Right? It gives 1 to 2 and 0 to 3. And we say that the entire tree is shattered by H if every branch has some function that realizes that agreement. And the Littlestone dimension is simply defined as a shadow tree, as the depth of a shadow tree of maximal depth. So in this case, the Littlestone dimension is 2. Why 2? Because we just found a shadow tree of depth 2. But we also need to show that there is no shadow tree of depth 3, right? Why there is no shadow tree of depth 3? So how much leaves do you need in a shadow tree of depth 3? 8, right? But we have only 4 functions, and we can't have 2 functions realizing 2 different branches because there's always a disagreement between 2 different branches. So the Littlestone dimension here is exactly okay, great. So why is the online learning rate with chain of thought for every t is at most the Littlestone dimension of t? So the idea is very, very simple. And it's based on this useful notion we call the t generation tree over an instance. So let's assume that in the first round, the adversary asks us about the instance, the prompt x1. We can construct the full generation tree of depth t that represents every possible chain of thought over x1. Okay, how? So from x1, we have 2 possible intermediate steps, either 0 or 1. So if we take 0, then the next instance, right, we append 0 to x1, and then we ask the question again, and we can go to either 0 or 1, and the same for here. So we can simulate all the possible chain of thoughts over x1. So this is called the generation tree of depth t for x1. And on every branch, we can, at the bottom of the branch, denote as f x1 and the labels of the branch as the subset of f of all functions that agrees with the branch. Now the simple claim is that if we look at the Littlestone dimension of those are called version spaces. Version spaces it's a subset of the class that agrees with every branch. So there is at most one version space, at most one branch, for which the subset of functions that agree with the branch has the same Littlestone dimension as the original class, which in this case we took the class of 2 Hamming balls, which has Littlestone dimension 2. It's easy to see because you can only put 1 in at most 2 instances. So the claim is that there is most one branch for which the version space is the same as the Littlestone dimension of the original class. And the algorithm would just be the following. So we calculate the Littlestone dimension at the bottom of each branch. And then for the one that maximizes it, we take the final bit of this chain of thought, and this is our prediction. Now, let me just explain why is this claim true, why we just have one branch with Littlestone dimension 2. We're out? Okay. Yeah, okay. So I'll finish. So basically, if we have such 2, you can verify it there after that yourself. If we have both such branches, then we can take x1 or some other instance and construct at the bottom of edge 0 a depth 2 shadow tree, and also here, and then we get a contradiction because we have a shadow tree of depth 3 which contradicts the definition, and therefore this claim is true. And basically the conclusion is that after every time we make a mistake, since we predicted the maximal one, the Littlestone dimension must decrease, so we make at most Littlestone many mistakes. And now we just need to show that the VC of the end-to-end class grows at least as log t, so I'll just say the proof idea. The proof idea is to take the following set of instances. It's for any arbitrary, never mind, choose an arbitrary x, and think of the set of instances as x and 0 to the something between 0 and t minus 1. And we now take t many functions, and independently, for every instance and for every function, we let f on the instance to give, we let it to give 0 with probability at most 1, 1 minus 1 over t, and 1 only with probability 1 over t, except for the last instance. So this is a random construction, and what we get from this construction is that you can verify the Lilston dimension with high probability is going to be 1. But this is the less interesting part. The more interesting part is that the VC of the end-to-end will be at least log t. And why does this happen? Because we also have a branch that keeps almost all of the functions, because on the green branch, every instance is received 0 by a fraction of 1 minus 1 over 2 of the functions. And after t steps, we get 1 minus 1 over 2 to the t, which is a constant fraction. And when we sum all of those branches that ends with 0, we also get a constant fraction from relatively similar reasons. And therefore, after every split, we maintain a constant fraction of the class. So we can repeat this for log f many times, which is log t. And we get that we can realize any labeling of any log t instance, basically. And that's it. So this is the separation, and you can see some future directions if you're interested. And thank you. Sorry for